Let's talk about calculus. Some consider it one of the greatest achievements of mankind when it comes to mathematics, learning to harness the power of the infinite in order to solve fundamental problems in physics and a host of other fields. Others consider it as just something that math departments use to torture undergraduate students. Either way, calculus is a rite of passage for aspiring mathematicians the world over. What many people don't realize, though, is how much the mathematics of change has undergone plenty of change itself. And it's still going through changes to how we think of it, even to this very day in this very millennium. As new mathematical tools are developed, those tools are often used to look back at old problems. What we're going to look at is one way that calculus is currently being rethought in terms of a truly bizarre and beautiful number system called the surreal numbers. When calculus first really took off in the 1600s, mathematicians like Isaac Newton and Gottfried Leibniz often talked in terms of the infinite, finding the slope of a curve by zooming in infinitely close, looking at a ratio of infinitely small rise and run, and calling that the derivative, finding the area of a curvy shape by splitting up a region into infinitely many, infinitely thin rectangles, and adding them all together smoothly, calling that the integral. But these calculations were based on some hand-wavy intuition. People knew that calculus worked, but nobody really knew why and how far we could push it. Eventually, it got to a point where Joseph Fourier started doing such bizarre things with infinite series when looking at problems involving heat and waves that mathematicians slammed on the brakes and decided they needed to formally pin down what was really going on. A number of mathematicians in the 19th century tackled this endeavor. Names like Augustin Louis Cauchy, Carl Weierstrass, and Richard Dedekind. What came out of all this was real analysis, a way of rephrasing those infinitesimal notions in terms of finite real numbers. For example, instead of saying a sequence of numbers gets infinitely close to a limit, real analysis rephrases it so that your distance from that limit is a real number, and you can make that distance as small as you want, provided you go far enough in the sequence. It's a lot of juggling of Greek letters, but it gets the job done. The development of real analysis taught us a lot about how numbers really work, and gave us rigorous definitions for many ideas that calculus relied on. The downside, though, was that infinitesimals became verboten. Intuitive notations like dy over dx were explained away as just symbols. Whenever you were doing real mathematics, you had to use real analysis. But the thing is, the idea of infinitesimals didn't die. Mathematicians would often think in terms of infinity and infinitesimals. They would just never admit as much in polite company. That is, until the early 1960s, when Abraham Robinson announced a new way of thinking about calculus by extending the real numbers. This wasn't really a new concept on its own. The complex numbers are also an extension of the real numbers, which you get by introducing a new number I, whose square is -1, and that allows us to take roots of negative numbers, as well as solve any polynomial equations. This time, though, Robinson added in infinitesimal numbers and infinite numbers, using a relatively new subfield of logic called model theory to make sure it met modern standards of rigor. The result was a larger number system called the hyperreal numbers, and calculus done using these new numbers came to be called non-standard analysis. Now, mathematicians could use those infinitesimals and actually mean them. The hyperreal numbers aren't the only number system containing infinitely large and small numbers, though. Another such system was developed by an English mathematician named John Horton Conway. Conway was a truly special type of mathematician who viewed mathematics as a fundamentally playful activity. While Robinson was publishing his work on non-standard analysis, Conway was creating and playing games and discovering some incredibly rich mathematics in the process, the kind of stuff that was often written about in Scientific American as part of Martin Gardner's column, Mathematical Games. The games Conway and his colleagues study became the foundation of what's today known as combinatorial game theory. Not the classical game theory that economists and political scientists use to model interactions between people as if they were games, but rather a kind that studies games like checkers, chess, and Go, where players take turns and there's no chance or hidden information. When Conway studied these combinatorial games, he started noticing something interesting. Numbers. I mean, of course there are numbers whenever games are involved, like counting or labeling pieces on the board. You'd be hard-pressed to find a game that doesn't use numbers in some way. But no, this was something more. Conway found a way to define numbers in terms of the games, creating a number system based on analyzing the possible moves in those games. And it ended up being a more expansive system than he ever could have dreamed of. Not only including all of the real numbers we're used to, but brand new numbers, infinitely large and infinitely small, much like the hyperreal numbers. Soon after, Donald Knuth, the inventor of the mathematical typesetting language LaTeX, wrote a book titled Surreal Numbers to introduce them to a wider audience, and the name stuck. The story had two students, Alice and Bill, who discovered some stone tablets while on a faraway island. These stones gave the construction of the surreal numbers, but phrased them as sort of a creation story. By the way, this may be the first time in history a work of fiction was used for the purposes of mathematical exposition. So let's assume the role of Conway and see how to create the surreal numbers ourselves. To start off with, we'll say that every surreal number can be thought of as a pair of sets, one on the left and one on the right. What we'll do is we'll create new numbers by putting old previously created numbers into those left and right sets, subject to some rules we'll see in just a moment. Our creation story starts on day 0, when no numbers have been created yet. With no numbers to work with, our only choice is to leave both the left and right sets blank. This blank blank pair is given the name 0. We've literally created 0 out of nothing, which makes a lot of sense. Next comes day 1. Now, since we've created the number 0 yesterday, we can use it to create new numbers today. For example, we can put 0 in the left set and leave the right set blank. Or we can put 0 in the right set and leave the left set blank. We could even try putting 0 in both sets, but it turns out that doesn't work. See, in order for a surreal number to be valid, there's a catch. According to the axioms we found on those stone tablets, every number on the left has to be less than every number on the right. But wait a minute, we're creating our numbers from scratch. So we actually have to specify what less than means in the first place. Say we have two numbers, which we'll call x and y. Each one has its own left and right set. What does it mean that x is less than or equal to y? The axioms specify that two things need to happen. First of all, y has to be greater than everything in x's left set. And second of all, x has to be less than everything in y's right set. Let's demonstrate this with an example, even though it'll use some numbers we technically haven't created yet, though we will soon. Let x be 1/2 and y be 2. In this case, 2 is greater than 0, the only number in 1/2's left set. As for 1/2, we don't even have anything to compare it to in 2's right set, so we're all good. That shows that 1/2 is less than or equal to 2, once those numbers have been created at least. But wait a minute, you might have noticed that we used the ideas of less than and greater than when we did this. How is that allowed? Well, the nice thing about this definition is that it bases everything on previously created numbers, so it can all be done by induction. What's even better is that the base case doesn't even usually need to be specified explicitly, since it usually boils down to those true by default cases that happens when the sets are empty, such as when you show that 0 is less than or equal to 0. Anyway, once we've got less than or equal to figured out, we can flip it around to define greater than or equal to. From there, we can say two numbers are equal when the less than or equal to relationship goes both ways. And that also lets us define less than and greater than on their own. Okay, so now that we know how to put numbers in order, we can agree that everything in the left set has to be strictly less than everything in the right set. And we can also show that the value of the surreal number itself falls strictly between everything in those two sets. We can also use our comparison to show that 0 blank is greater than 0. So we'll decide to call it 1. Why? Same reason we do anything in math, because it seems sensible and we just want to see what happens. While we're at it, we can also start defining operations on our numbers, such as negation, which we'll get by switching the left and right sets and negating each member. Notice once again that we're defining negation inductively in terms of previously created numbers. Using that definition, we can prove that 0 is its own negative, which we can then use to prove that the negative of 1 is blank 0. So we'll name that other number negative 1. Now it's day 2, and we have 3 numbers to work with, 0, 1, and negative 1. When we put them into sets, we end up getting 4 new numbers by putting them in various combinations. There are other possibilities as well, sure, but it can be shown that they can be simplified down to one of these forms. For instance, all we really care about is the greatest number on the left and the least number on the right. We can figure out what numbers these are once we define addition. To add 2 surreal numbers x and y, first we add x to everything in y's left set and vice versa, and put all those possibilities on the left. Then we add x to everything in y's right set and vice versa, and put all those possibilities on the right. Finally, we put those into our brackets, and that's our sum, though we might be able to simplify it. So using this definition, for example, we can show that adding 0 to any number gives itself, just like we'd expect. Any term that doesn't exist is just left out, and the rest is taken care of using induction. Okay, let's go back to day 2 and see what we can do. If we add 1 plus 1, we get our new number 1 blank. So we'll call that number 2. And its negative will be negative 2. Figuring the other one out is a little bit trickier. For that, we're going to need something called the simplicity rule. Remember when we noticed that each number fits neatly between its left and right sets? Turns out there's even more to it than that. It can be shown using similar inductive arguments that if you take any numbers and throw them into your left and right sets, making sure of course that everything on the left is less than everything on the right, the value that you get will be the simplest number between the left and right sets. By simplest, we mean in terms of when it was created, what we often call its birthday. 0 is the simplest number since it was created on day 0, which means it has a birthday of 0. The next simplest numbers are 1 and negative 1, since their birthday is 1, though neither is simpler than the other. And so on. In other words, we have what we call a partially ordered set, or poset for short. So for example, if we look at negative 1 and 2, the simplest number between them would be 0, since that's the one with the smallest birthday. Let's see how that helps figure out what that other number is. We already know that 0, 1 has to be between 0 and 1, so it has to be a fraction. Well, if we add it to itself, we end up getting 0, 1 in the left set and 0, 1 plus 1 in the right set. It might seem like we're out of luck, but remember that 0, 1 is less than 1, and that 0, 1 plus 1 has to be greater than 1, since 0, 1 is greater than 0, it's positive. So by the simplicity rule, the simplest number between these two has to be 1. That means that 0, 1 is in fact 1/2, which means negative 1, 0 has to be negative 1/2. Take a look at what's happened here. Once we set up some of these rules, figuring out which numbers are less than others, deciding how to negate and add numbers, the number system takes on a life of its own. Each day, new numbers get created, and they slowly expand outward and then fill in the gaps in between. That being said, the definitions probably seem kind of arbitrary. I mean, where did that definition for addition come from in the first place? If we're being honest, those kinds of definitions usually start by first noticing the kinds of properties we want things to have, based on how we think they should work, and then turning those properties on their heads and making them the definitions, in hopes that they continue to give us what we want. That's how we can define not only negation and addition, but even multiplication of surreal numbers, based on the members of their left and right sets. And if we go ahead and define reciprocation, then we've got subtraction and division as well. And it turns out that all these operations follow all the same nice rules as the ones we're used to. Anyway, we can continue this creation process as long as we'd like. we eventually get all the integers, as well as all the fractions whose denominators are powers of 2, like the tick marks on a ruler. These numbers are called dyadic fractions. Every whole number birthday has a whole bunch of surreal numbers created on that day. But then something amazing and kind of inspiring happens. See, in math, just because you've done something infinitely many times doesn't mean you can't keep pushing forward just a bit more. Conway was interested in a particular kind of number that lets you do this: ordinal numbers. Unlike cardinal numbers, which are used to count how many items there are in a set, ordinal numbers are used to label those items when they're placed in order. Think like the ordinal numerals 1st, 2nd, 3rd, as opposed to the cardinal numerals 1, 2, 3. Just like with cardinal numbers, there are infinite ordinal numbers when you have an infinite list of objects. The first one is called omega, which comes after all the natural numbers. But unlike with cardinal numbers, we can keep adding more onto the end of the list, giving us omega plus 1, omega plus 2, and so on, each one strictly larger than the last. After a while, we can have omega plus omega, or omega times 2. From then on, we can keep adding on more copies of omega, collecting together multiples, or even powers. You can even do arithmetic with ordinal numbers, though you have to be careful. They follow some weird rules when it comes to addition and multiplication. Since our birthdays form an ordered set, we can continue to use ordinal numbers as birthdays. And on day omega, there's an explosion of numbers. First of all, we get the entire rest of the real line, both rational and irrational numbers, because they all can be approximated on the left and right by closer and closer dyadic fractions. Think of it like binary. But that's not all. We also get our first infinite surreal number, greater than all of the integers, which we call omega. And we also get our first infinitesimal surreal number, less than all of the positive fractions, but greater than 0. And we call that one epsilon. Remarkably, it can be shown that these two multiply to be 1. Of course, we also get negative omega using our rule for negation, as well as negative epsilon. If our birthdays are ordinal numbers, we can keep going again. The next day we get omega plus 1, but also omega minus 1, as well as 2 times epsilon, and epsilon over 2. If we continue the process further, we get more and more exotic surreal numbers. Just about any way you can algebraically combine these infinities and infinitesimals together, you can make a surreal number out of it. Continue this for all possible ordinal number birthdays, and we finally end up with the entire class of surreal numbers, which we give the name NO as an abbreviation for number. And that class forms an ordered field, which means that they all fit on a very long number line, even the infinities and the infinitesimals, and that the operations of addition, subtraction, multiplication, and division work exactly the way we're used to, which makes them easier to work with than the ordinal numbers. Wait a minute, classes? Are those the same thing as sets? Well, not quite. See, when you start talking about a number system as fundamentally large as the surreal numbers, or even the ordinal numbers for that matter, you run into issues if you try to think of the entire collection as a set in the strictest sense, because sets have to follow some strict rules of their own. That didn't always used to be the case, of course. It used to be that sets could be just any old collection of objects that you could define. But as is usually the case, logicians, such as Bertrand Russell, had to come along and poke holes in the definitions, finding all sorts of interesting paradoxes and contradictions that could come from so naive a definition. Russell's paradox involved defining the set of all sets that don't contain themselves, and then asking whether that set contained itself. That's sort of the set-theoretic interpretation of the barber paradox, where a town has one barber who shaves all and only the people who don't shave themselves. The question is, then, who shaves the barber? To try to fix these paradoxes and put set theory on a more firm logical footing, Ernst Zermelo and Abraham Frankel put together a set of basic axioms that could be used to describe how sets should act. But they were careful about how they wrote them to make sure that those paradoxes wouldn't happen. The resulting set of axioms is called ZFC, which stands for Zermelo-Fraenkel set theory, along with the axiom of choice. That's an extra axiom that assumes you can take an arbitrary collection of sets, choose one thing from each set, and put them all into another set. The axiom of choice is somewhat controversial. Some mathematicians like it because it's useful. After all, it was essential to Robinson's development of the hyperreal numbers. But others are wary of it because it can lead to some pretty weird stuff. The ZFC axioms cover issues like how to tell when sets are equal, and how to create new sets out of old ones in a variety of ways. The one that avoids Russell's paradox is the axiom schema of specification. It states that you can't just willy-nilly make a set of all sets that satisfies some property, like containing themselves. You have to start with a set to begin with, and then look at the subsets of that set that have that property. In other words, you can't just say the set of all sets that. You have to say the set of all subsets of X that. Another useful axiom is the axiom of infinity, which essentially says that we're allowed to consider the natural numbers as a set. What's neat is that ZFC also provides a way to construct the natural numbers, thanks to John von Neumann, much like we did with the surreals. We start with 0 as the empty set, and then each successive natural number is defined as the set containing all the previous numbers. So 1 is defined as the set containing 0, 2 is defined as the set containing 0 and 1, and so on. We know that each of these finite numbers is a set because of the axiom of union. But what the axiom of infinity does is assert that once we have all of these numbers, we're allowed to count it as a set. But our construction doesn't have to stop there. What's to stop us from continuing the exact same construction to get more and more numbers? That, in fact, is exactly what the ordinals do. Each time we repeat the construction, we're guaranteed to get a new set. And by using the other axioms, we can end up with any ordinal number we want. The problem comes when we try to consider a set of all ordinal numbers. It seems like a reasonable enough concept to have. But what if we used our rule again? Then we'd get a new, even larger ordinal number. But that would contradict the idea that we had a set of all ordinals in the first place. Again, that idea of unrestricted comprehension, the set of all sets with some property, makes us run into paradoxes. So under the axioms of ZFC, we don't allow the existence of a set of all ordinals. But at some point you find yourself saying, gee, I really wish I could talk about the collection of all ordinals and call it something, even if it's not technically a set. Enter NBG set theory, named for John von Neumann, as well as Paul Bernays and Kurt Gödel. In NBG, we introduce the notion of a class, which is more broadly applicable than the idea of a set. When a collection is so large that calling it a set would produce a paradox, such as the set of all sets with some property, then we call it a proper class, since it can't be a set. All sets are classes, but not all classes are sets. So we can say that there's a class of ordinal numbers, a proper class that is, which we usually call ON, short for ordinal numbers. How about the surreal numbers? Well, remember that each surreal number has a birthday, which is an ordinal number, and that one of the numbers created on that birthday was that ordinal number. That means the surreals have the ordinals living inside them, so they're way too big to be a set. That's why we say that the surreal numbers form a proper class as well. In fact, the surreal numbers contain a whole lot more than just the real and ordinal numbers. There have been many number systems created with infinite and infinitesimal elements in them. The surreal numbers actually contain all of them. And it's actually been shown using NBG set theory that the hyperreal numbers are in some sense isomorphic to the surreal numbers. That's why Conway said that the surreal numbers encompassed all numbers great and small. Okay, so now we've got a good feel for what the surreal numbers are, and just how many of them there are. But how are they supposed to help us understand calculus? To answer this question, we need to see how the surreal numbers compare with the real numbers we're used to. See, one of the difficulties in making calculus rigorous back in the day using real analysis was actually figuring out what the heck real numbers are in the first place. It's not enough to just say, oh, everything on the number line, and call it a day. One of the main ways we do this is thanks to Richard Dedekind, who had the idea of defining real numbers by partitioning, or cutting, the rational number line into two pieces, where everything on the left side is less than everything on the right side. For example, we could put all the negative rational numbers on the left, and the rest of the rational numbers, all the non-negative ones, on the right. Notice that the right set has a smallest member, namely 0. So we'd say that our cut is identified with the number 0. But we could also cut the line in a different way, say with the left set containing all the negative rational numbers, as well as the positive rational numbers whose square is less than 2. And then the right set would contain all the other rational numbers. This time, the right set doesn't have a smallest element, since there's no rational number whose square is 2. And likewise, the left set doesn't have a largest element. So we found a sort of gap in the rational numbers. That cut is therefore representative of an irrational number, in this case, the square root of 2. If we look at all the possible cuts we can make, we get every possible rational and irrational number, which gives us all of the real numbers. By filling all of these gaps, we've made the real numbers complete. And the fact that the reals are complete is what allows us to do the things we need to do in calculus. Now, wait a minute. Didn't that whole everything on the left is less than everything on the right business look kind of familiar? That's almost exactly what we did when we constructed the surreal numbers. But since we've allowed for infinitely small and infinitely large elements, the surreals can fit numbers in gaps that the real numbers didn't even know they had, even more densely than the reals themselves. But what's even more surprising is that because of our unique fractal tree structure, even with this whole keep going to infinity and beyond deal, at the end of the day, after all ordinal number birthdays, we still have gaps. Lots of them. Anytime we can cut the surreals into two classes so that no member of the left class is greater than or equal to the right class, we've found a gap. And we like to say that they all have a birthday of ON, which we'll start pronouncing on from now on, since that's when we found the entire class of surreal numbers. So the surreal numbers are not complete. Some of these gaps have special names. For example, we could put all the surreals into the left class and leave the right class blank, which gives us a gap that's greater than all surreal numbers at the far right edge. Following our usual naming convention for numbers, we'll call this gap on, since that's its birthday. Remember though, on is not an ordinal or surreal number. On the other hand, we could put all the surreals in the right class and leave the left class blank, which would give us a gap at the far left edge of the surreal line, less than every surreal number. This would seem to be the negative of on. So, you know what? We'll call it off. Yes, that's seriously what it's called. Who says mathematicians can't have a sense of humor? Another interesting gap is the one we get by putting all the finite numbers or the negative numbers on the left, and all the infinite and positive numbers on the right. That gap we usually call infinity, since it acts a lot like the infinity we're used to from real analysis. There are a whole bunch of other gaps as well, each of which can be represented as some kind of sum of surreal numbers. But just like with the real numbers, we can just take all of those gaps and throw them in with our surreal number system, forming what's called the Dedekind completion of the surreals. Okay, so now we know a little more about our numbers and the gaps between them, and what it means to complete the surreal numbers by throwing in the gaps. What does that get us? Well, suppose we have a sequence of surreal numbers. What is a sequence anyway? Usually we think of a sequence as a function from the natural numbers to any given set. But once we've got ordinal numbers, we can talk about the omega-th term of a sequence, then the omega plus first element, and so on. When we index our sequence with the entire class of ordinal numbers, we say the sequence has length on. But we might run into a situation where we have a sequence of surreal numbers whose limit isn't a surreal number, which could be a problem for some of our limits. So by working with the Dedekind completion of the surreals, we ensure that the limits exist whenever they should, though we're careful not to say that such a sequence converges when the thing it approaches is a gap. There's a bit of an issue though. We'd like to make sure that our limits can also be expressed in terms of a left set and a right set. But if we allow our sequences to be indexed over the ordinal numbers, we might end up with a situation where at least one of these collections has to be a proper class. That's a bit of a problem, because all of our surreal numbers were defined in terms of their left and right sets. We can get past this by taking another page from Dedekind and defining what's called the Dedekind representation of a surreal number or a gap. Given a surreal number or gap x, what we do is to cut the surreal line into all the surreal numbers less than x and all the surreal numbers greater than x. If x is a surreal number, then it'll fall neatly between the left and right collections, at least one of which will be a proper class. But if x is a gap, the left and right collections together will form the entire surreal line. Luckily for us, all of our previous definitions involving comparisons and algebraic operations can be modified to work with Dedekind representations, and they match what we're used to. Now we're free to use classes instead of sets, and everything will still just work. Let's look at how to use these Dedekind representations to evaluate the limit of the sequence 1 over n, where n ranges over all the ordinal numbers. So the first element is 1, the second element is 1/2, the omegeth element is 1 over omega, also known as epsilon, and so on. Here's what we'll do. First, we'll view all the terms as their Dedekind representations. Then, we look at the intersection of all the left and right collections. So in this example, we get that the intersection of all the left sets contains all the numbers less than or equal to 0, and the intersection of all the right sets contains all the numbers greater than 1. Now, drop the first term and recompute the intersection. The left intersection remains the same, but now the right intersection contains all the numbers greater than 1/2. And we can continue on in this manner, once for each ordinal number term. Okay, next we look at the union of all of these intersections. Our left union contains all the negative surreals and 0, and the right union contains all the positive surreals. Notice that the least upper bound, or supremum, of the left union is 0, and the greatest lower bound, or infimum, of the right union is also 0. If these two things match, then that number or gap is called the limit of our sequence as the index approaches on. What's truly remarkable is that it can be shown that when the limit of a sequence is a surreal number, this definition of a limit perfectly matches the one from real analysis, namely that the limit of a surreal sequence is L whenever for every positive surreal number epsilon greater than 0, that's an arbitrary epsilon by the way, not the 1 over omega kind of epsilon, there exists an ordinal number big N, such that the distance between A sub n and L is less than epsilon, whenever n is an ordinal number greater than big N. Be careful though. This definition doesn't match for sequences that approach gaps. For example, if we consider the sequence omega to the 1 over n, then the limit comes out to infinity. That's the gap infinity, by the way. But we can't make the distance between the sequence and the limit as small as we want, because it'll always be greater than infinity. Our foray into sequences also leads us to take another look at what it means to be complete. Unlike Dedekind, who characterized the completeness of the reals in terms of cuts and gaps, Cauchy defined completeness in terms of sequences. In real analysis, a Cauchy sequence is a sequence for which the terms get arbitrarily close to each other, staying within any tolerance you give provided you go far enough in the sequence. The fact that every Cauchy sequence of real numbers also converges to a real number is what leads us to say that the real numbers are Cauchy complete. But remember that the surreal numbers were not complete according to Dedekind's definition. So it likely comes as no surprise that they're not complete by Cauchy's definition either. For example, take this sequence here, summing up larger and larger powers of epsilon. It's a Cauchy sequence because given any surreal tolerance, we can find a point far enough in the sequence such that any two terms after it will be within that tolerance of each other, But the limit of this sequence is actually not a number, but a gap. However, we can fix this by making a few particular definitions. First of all, we'll extend our Dedekind cut definition so that either of our left and right classes is allowed to contain its endpoint. Second of all, we define a surreal gap as a Dedekind cut of the surreal numbers that isn't equal to a surreal number by one of the two new definitions we just made. By making these restrictions, we can guarantee that Cauchy sequences either converge to a surreal number or approach a surreal gap. Alright, we're starting to get somewhere. Now that we've got sequences and their limits taken care of, we're almost done laying the groundwork to handle calculus. Usually, the next thing we would do would be to move from sequences of surreal numbers to functions of surreal numbers, seeing what happens when we let a sequence of inputs approach some number, and checking whether the corresponding sequence of outputs approaches a limit of its own. This is important for talking about whether such a function is continuous. But once you start talking about continuity, you start needing to talk about topology, and that leads to some issues of its own. Usually, if we have a set X, we say that a topology on X is a collection of subsets of X, following three basic rules. It has to contain the empty set and the entire set X, it has to be closed under arbitrary unions, and it has to be closed under finite intersections. The elements of this topology are called open sets, and they satisfy our usual intuition about open sets we're used to from the real numbers. But the surreal numbers form a proper class, so we have to slightly modify our definition to fit them. When we define a topology on the surreals as a collection of subclasses, we say it needs to contain the empty set in the entire class, but we only require it be closed under unions indexed over a proper set, not necessarily any arbitrary class. This is necessary to make sure that connectedness and compactness work the way we want them to. Finally, the finite intersection part of the definition is just fine as is. From here, we can define a topology on the surreal numbers based on open intervals, just like what we do with the usual Euclidean topology on the real numbers. First, we can define open intervals as those intervals whose endpoints are either surreal numbers or on or off, but do not contain their endpoints. And then, a subclass of surreal numbers is open if it can be written as a union of such open intervals, once again as long as that union is indexed over a proper set. From there, as long as we include the empty set, we do in fact have what's called the standard topology on the surreals. And finally, once we've got a topology, we can define continuity, the same way we always do in topology. Namely, a function is continuous if, given any open class of surreals, the class of surreals that map to it, the preimage, is an open class itself. One other thing we do have to be careful of is that one of the usual ways of talking about openness doesn't quite work anymore. Often in real analysis, we say that a set is open if every point in that set has a neighborhood contained in that set. But this isn't true with our definition. For example, the class of numbers between infinity and on satisfies these neighborhood requirements, but it can't be represented as a set indexed union of open intervals. So it's not actually open. This property is actually a weaker property called local openness. And while every open set is locally open, the converse isn't true. Okay, wow. This is a lot of heavy stuff we've talked about. So let's take a step back to see what we've done. In order to make sense of sequences, limits, and functions, we've had to slightly modify how we think about surreal numbers and gaps to be very similar to how Dedekind constructed the real numbers. And we've had to be very careful with whether we're dealing with sets or classes. But by making those reasonable restrictions, the world of calculus opens itself up. First of all, we can now evaluate limits of functions in a very similar way to how we evaluate limits of sequences. In fact, the left and right classes beautifully describe the left and right-hand limits. And if that limit is a surreal number, we can also use the epsilon delta definition, except that those epsilons can be actual infinitesimals if we want. We can even get those familiar limit laws for addition and multiplication of functions. And since derivatives are defined as limits, We can now define the derivative in terms of limits, just like we normally would. Except that once again, we can imagine those changes in x and y as being honest-to-God infinitesimals, but in a rigorous way. We can establish a relationship between limits and continuity, though it's a slightly weaker one. When a function f defined on a locally open class has the property that the limit as x approaches a is equal to f of a, we only call f weakly continuous at a. Every continuous function is weakly continuous, but not the other way around. One of the most surprising things is that we actually get a surreal version of the intermediate value theorem. The IVT for the real numbers depends on their completeness property. But by making the restrictions we did on the surreals, we still get the IVT, even though the surreals are not complete. Awesome. What about integrals? And series? Well, actually, we're still working on those. They're a bit difficult. The usual ways that we do things like defining series as limits of sequences of partial sums get a little hairy because of gaps. We know how to make power series work with some very nice functions such as geometric series, but other power series such as e to the x still elude us. And we can prove that the fundamental theorem of calculus works if we have a good definition of integration. But that consistent definition of a definite integral is still something we're working on, because those same issues with infinite series cause problems with Riemann sums. Conway himself struggled with getting integration to work right, noticing that by his original definition, the integral from 0 to omega of e to the x dx comes out to e to the omega, not e to the omega minus 1 as expected, though authors within the past decade have since found some ways to potentially resolve his issue. So yeah, Surreal Analysis is still a work in progress. But you know what? I think that's pretty awesome, and pretty humbling, and pretty inspiring. It tells us something about the state of mathematics. Way too often does mathematics get this reputation as something that's over and done with, already figured out and just passed on through textbooks, lectures, and mind-numbing AP tests. And calculus is quite often one of the biggest culprits for giving this impression. But here, we've seen how mathematics and even calculus can still be a creative and, dare I say it, joyful endeavor. I mean, we literally created numbers from nothing, using techniques that originally came from analyzing games, had to make decisions about how these new numbers should behave, revised our definitions as we discovered all sorts of new quirks that our decisions led to, and even after all that, we still have a ways to go on getting some of the most basic notions of calculus to work. It just goes to show how the surreal numbers are a rich and vast landscape just waiting to be explored. The creation story of mathematics is far from over.